Greetings everyone. Welcome to tinyML talk series. Today we have these two interesting topics for the talk. My name is Rajan Bhatt. I am Director of Machine Learning Division in Kixo, and I will be moderating the talk series today. Before we begin the talk, I would like to thank tinyML talk sponsors. ARM is our strategic tinyML partner. We have other sponsors, Edge Impulse, Kixo, SynSense, DeepLight, Maxim Integrated, and Reality AI. Additional sponsorships are available. Please contact BT at tinyml.org for more information. We have next series of talks available on Tuesday, December the 8th. We have our first speaker on December 8th, Ian Campbell from OnScale. He would be speaking about training embedded AI and machine learning using synthetic data. And our second speaker will be Sakya Singh Dasagupta. He is founder and CEO of Edgetronic Inc. And he would be speaking on using AI to design energy efficient AI accelerators for the edge. Please contact talks at tinyml.org if you are interested in presenting the topics. Our next topic for the day is from Brian Turnquist and Rodney Dockter from the Boon Logic, and their topic is a complete machine learning based anomaly detection pipeline for microcontrollers. They call it AMBER. Okay, we have a brief biography of the speakers. Brian Turnquist has been working in the topics of machine learning and AI since past 20 years and has developed many novel algorithms for automated clustering of biological signals in real time. He is a CTO of Minneapolis-based tech startup Boon Logic, and has been also the visiting researcher at the University of Nuremberg and Heidelberg, and a tenured professor at Bethel University. His PhD is from mathematics from the University of Maryland, and with many referred publications in neuroscience and mathematics. And he will be joined by his colleague Rodney Dockter. He's an engineer with broad experience in machine learning, artificial intelligence, and the development of systems for the industrial automation and robotics. And Rodney is the director of computer vision at Minneapolis startup Boon Logic and a lecturer at the University of Minnesota. And he holds PhD in mechanical engineering from the University of Minnesota. So Rodney and Brian, to you.
Thanks, Rajan. Yeah, just a quick overview here, and then we'll get into our slides. So what we want to do this morning is present a comparison of AMBER to what we see on the talks as a common tinyML approach, and we think about the difference and contrast between those approaches. We have three examples. One is output current of a motor and drive system, vibrational example, and also EEG in brain. So after we look at the examples, we'll look at a core algorithm benchmark against k-means, and then I'll hand it over to Rod, and he'll talk about the benchmarks on ARM Cortex M7 and M4. And then we'll just have some time for a summary and some questions. All right, so just a couple things to set the table here. AMBER is an anomaly detection technology for single sensor and sensor fusion data streams. AMBER can be trained and deployed entirely on the microcontroller without compute support from gateways of the cloud. AMBER is not a neural network, and it's not based on neural networks. AMBER is based on unsupervised machine learning segmentation of the sensor signal. And finally, AMBER is an application of our core segmentation algorithm, the Boon Nano, which I'll say a little more about later. So I think those of you who have been attending the tinyML talks, here's a very rough flow diagram for developing solutions for tinyML. You're going to have in step one some kind of recording step where you acquire representative data from your sensor source, whatever that might be. And that is going to be possibly labeled if it's a supervised type solution, and that will be done on a CPU general compute platform. And then the model building itself will be done either on a desktop type GPU enabled computer, or it can be done with cloud resources to build the inference model and do the pruning. And then the fourth step is then to deploy the custom model out to the MCU to begin the monitoring process with the constructed model. So I think for those of us who watch and participate in the tinyML, this is a typical kind of pipeline that we see. So AMBER applied on a microcontroller looks like this. First of all, I want to point out kind of here on the right side that this is happening entirely on the microcontroller. So there's no cloud resources being applied, no gateway resources being applied. We have our initial step where the sensor is acquiring the single sensor data either through analog or digital channels. And we do an auto-tuning stage initially, where we optimize the hyperparameters of the Boon Nano, the core algorithm. And optimizing min and max is a relatively routine operation. I think that all of us do when we build models for sensors. And then finding the other optimal hyperparameters is a much more sophisticated type of activity. It's it's something like what you see with k-means in an elbow operation, where you're trying to find the optimal clustering topology to represent the data that you're acquiring at the time. So that's the auto-tuning phase. This can typically be done in about 1,000 samples. 1,000 to 10,000 samples is usually sufficient to do the auto-tuning. Once the auto-tuning is complete, then the hyperparameters are instantiated on the Boon Nano, and we start learning from the sensor data stream. And what's happening in that case is as you see on the horizontal axis, these can be thought of as sensor values. And what you see in the vertical axis is cluster count. So we're adding clusters as we go along, as needed, in order to characterize and capture the underlying topology within the data set as n-space clusters. And then finally, once the learning is complete, as you see here, it's kind of leveling off at the end. And this indicates that there are sufficient clusters now to characterize this particular data stream. Then it automatically transitions over to monitoring mode, where we do the segmentation and the anomaly detection. And so just to reemphasize that this entire pipeline is happening on the microcontroller, and it does this, all these steps autonomously, transitioning from one step to the next and doing the training at each step in real time. As the samples come in, once it's in the monitoring mode, now you have a number of analytic outputs that are relevant. Those of you who are familiar with unsupervised machine learning and segmentation understand that each cluster has an ID. And so one of the core analytic outputs is for every sample that comes in, you're getting a cluster ID of the recent subsignal up to that moment. And that's happening once for each sample. These other machine learning outputs are also available for each sample. The one we'll focus on for this talk is the anomaly index. So this is a frequency-based anomaly index of the signal, frequency referring to the statistical idea of frequency of occurrence. And so the sort of basic idea that everyone has about what an anomaly is, it's an infrequently occurring subsignal within your signal. But there's other types of anomalies. There's ones that are occurring extremely often, like much more often than others. And another definition of an anomaly is one of distance. So a commonly occurring subsignal that within n space is significantly different from the rest of your subsignals. So for this talk and for these applications that I have examples, we'll focus just on this idea of infrequency, and that's the anomaly index. Some of these other indexes here are also available. So the first example here, this is data that was collected during the customer engagement. These were Allen Bradley drives and motors. We were running a bottle capping profile. So you sort of imagine a production line with a motion profile that's screwing a bottle cap on bottles as they pass by. And for our input into AMBER, we use the PLC output current tag. The compute resource we were using here was what was available on the customer's compute module, which was an Intel Atom dual core 1.46 gig processor. On this processor, for 1,000 samples per second, AMBER was consuming only 4% of that processor. One of the core questions around this engagement was, do universal models work? And this has been a question that's been kind of popping up and has been talked about a number of tinyML talks, and it's also obviously a big topic within the IoT community as well. And so part of this customer engagement was a controlled experiment using this motor and drive configuration, an identical motor and drive configurations. And the short answer here is that no, universal models don't work. Every asset is unique and needs to have a model trained uniquely for that asset in order to get best detection and the lowest false positive rate. Another goal of the engagement was detection of transient drift and shift anomalies. And so let me just get to the video here. What you're seeing at the top row here is the output current. What you see below it is the number of clusters. The horizontal axis is time in seconds. So you can sort of imagine with each one of these surges in the output current that you're imagining a bottle cap is being screwed on. And what you see right away is that AMBER is adding clusters as it works through these different signals and sort of sees not just similarity, but also slight variation from normal. And so what we're learning with AMBER is normal variation in compliance signals. So let me just start this playing here. All right, so as you look at the cluster count, it's growing very slowly. AMBER has detected most of the clusters that are here, but every once in a while there's some small variation that it hasn't seen before. As you look down to the bottom, you see one of our core analytic outputs, the anomaly index, and this ranges from 0 to 1,000. And when it sees something in the signal that's atypical based on the model that's built, it spikes very high. Anomaly detection threshold values of 850, 900 are pretty universally useful. Here you see the learning is complete, and now we switch into monitoring phase. So this is the third of the 3 phases that we're in now. So there'll be no more clusters added. Anything that's seen that's outside of the existing model is an anomaly. Here's the first one. And let me just make a comment about this here. So we take a look at this signal. This is a small sub-signal. If you're trying to detect this type of deviation based on threshold, you would not detect it. It's very difficult to detect. And actually, FFT-based detection of this type of transient anomaly is also extremely difficult because of the windowing that's done with the spectral analysis. We do use FFTs in some applications. We can use it, but this is being done on the raw time domain signal. And let me just get this rolling again here.
So, Brian, it is probably relevant to ask one question right now.
Yeah, sure, absolutely.
Is this the number of clusters? It seems like very high number of clusters, around 90, 91. How many clusters we have here?
We have around 100, and if I'm reading my tick marks properly, 162 clusters.
Okay, okay. So which cluster, that's one of the questions here, that which clusters do represent anomalies and which ones represent normal?
So for this particular, this is using the anomaly index. And so the anomaly index is looking at the size of a cluster. In other words, the number of vectors that were assigned to it during the learning phase.
Okay.
So if there were very few vectors assigned to it during the learning phase, or if during the monitoring phase you see a vector that doesn't fit any of the existing clusters, those are both anomalies.
Okay.
Mm-hmm.
Okay.
And I've got two more examples here. So let's, I'll just move to these other ones. And yeah, I'd be glad to take questions as we go along here. This is a synthetic data source. We've dealt with many vibrational data streams. And as I said, we can analyze those with either analyze the power spectrum or the time domain signal. I made a synthetic one here so that I could kind of group together a number of different types of anomalies. So this has a number of principal frequencies, some Gaussian noise, and it has transient anomalies at 675 seconds. I'm just going to jump right into it here. You see already that the learning is, we do have a large number of clusters, 150. This is not a large number of clusters for us. For our technology, we often go up into the hundreds of clusters, even into up to 1,000 or more clusters. Rod will talk about some of the constraints on the microcontroller during his portion. So here we have, here's an anomaly that you see down here, very difficult to see in the raw data signal. These are the types of anomalies that are essentially invisible to the human eye. Right. I use the first example because it's easy to see what's going on. Yeah. Now let's look at some real cases, right, where here's another anomaly that's been introduced, and then we come up here at 90 seconds. We have what I would call a shutter in the vibrational signal, which would be 2 seconds of a high frequency component that comes in and then drops back out again. And then that same frequency component will come back in at 105 seconds.
Right. One more quick question, Brian. Yep. Is this anomaly detection threshold, which is 850 currently, is this something can be configured?
It can be configured, but because of the way our technology works, it is set automatically based on the training that happened. Yes.
Okay.
Last example here. There's a very interesting MIT-based data set for machine learning applied to epileptic seizure detection. And in this particular example, what they were doing was they had 23 cranial electrodes applied to patients all with epilepsy, and they're using an SVM to try to train a neural network in order to detect seizures. Well, a seizure is an anomaly in the normal brainwave patterns of an individual. One of the things they point out in the paper is that what looks like seizure activity in one person may be normal in another person, and vice versa. So this is a classic universal model question And again, pointing to the idea that models need to be trained for individual endpoints, even if that endpoint is a person. So let me start this off here. You can see the cluster count growing. This is the EEG signal that you see at the top from one sensor. You see it grow a little bit there as this kind of unusual, even 13, 14 seconds in, the cluster count is growing. Jump ahead here to 990 seconds. Here we see at this point that the learning is automatically turned off, and now we begin this monitoring phase. Kind of watching the anomaly index at the bottom. And we jump ahead. Here's one of the first labeled disturbances in the EEG signal coming up here, right there. Okay, again, very difficult to detect using a threshold-based technology, and basically impossible, I think, to detect using a threshold-based technique. They were able to detect it using an SVM, but that SVM had to be trained for each person, and of course trained offline from the data. Here's another episode. Okay, so that's the third example, just to give you kind of a flavor for what AMBER is and what it does. I just want to say a few words about the speed of the core technology, and then I'll hand it over to Rod for a few comments about the benchmarks. So this comparison was done to k-means, which is a very familiar technology. I've used k-means most of my career. K-means is a distance-based segmentation technology using L2 distance typically. Boon Nano uses L1 distance. They produce very, very similar clustering results in practice. The Boon Nano is much faster than k-means. It's roughly 1,000 times faster on comparable technology, a comparable platform, and also much smaller in terms of the models that it builds. And so we can actually use and get up to 1,024 clusters on a microcontroller. You can see the inference time here shown. This was done on an AWS EC2 instance. We did not want to try to implement k-means on a microcontroller, so we ran our benchmark in the cloud. And you can see here the k-means on the ML pack, which is an excellent, very, very high performance k-means for C++ based environments. You know, it has a growth constant of about 2.4. This is as cluster count increases, right? So as cluster count increases, the search space increases, and the per pattern inference time in microseconds goes up. We see k-means growing at 2.4. Boon Nano is also growing, but its growth constant is about 1,000 times smaller. So that's a core benchmark, and it's really the enabling technology for AMBER. So with that, I'll hand it over to Rod and let you talk a little bit about the benchmarks.
Yeah. So my name is Rodney Dockter. Like Brian mentioned, I'm one of the embedded engineers here at Boon Logic. So I'm just going to briefly talk about some of the details regarding our microcontroller platform that we use for our embedded AMBER product. And then I'll also briefly show you some of the performance benchmarks that we can achieve with AMBER on our embedded platform. So the processing chip that we focused on was an ARM Cortex M7, specifically from the ST Micro H747 family. So this specific processor has a max clock speed of 480 megahertz and 1 megabyte of internal RAM. The board we're using also has a external SD-RAM chip with 8 megabytes of RAM, which I'll show you kind of becomes important for our use case. I'll also mention that this board has wireless radio capabilities, Wi-Fi and Bluetooth, but during normal operation, we're not actually enabling those or turning them on at all. We really only enable them when we need to send an anomaly alert to an operator if we're running in a industrial factory or those sorts of environments. And then speaking of battery life, we're targeting a lot of battery supported applications, especially if we have relatively low frequency sample data. However, if we're talking about some of these super high frequency samples, then external power likely becomes necessary. So on the right here, we have a video of real-time anomaly detection happening on board this platform, on board this AMBER platform. So the data here is being sent via serial so that we can monitor it and see the raw signal and the anomaly index values. But obviously normally we wouldn't have the serial enabled for that. So the signal that we're looking at here is the same current signal from those Allen Bradley motors that Brian discussed earlier. Here though, we're reading in that data directly into the SD microchip via the analog ADC. We can also support I2C, SPI, those kinds of digital formats. So kind of the first step in the pipeline is to just acquire the next sample. We add that into our feature vector, and then we start clustering and computing anomaly indexes. So on board this chip, we have those same early auto-tuning and learning phases. But what you're seeing here is once those are completed, we're just looking at that raw data and looking at the anomaly index. So in normal operation, what we would do is, again, kind of threshold that anomaly index. And if it spikes, we'll alert an operator via that wireless radio. So Brian, if you want to go to the next slide. Yeah, so just quickly, we'll go through some of the performance benchmarks for the AMBER platform. So using our standard M7 platform with that 480 megahertz clock, we can achieve inference times around 40 microseconds. And again, given kind of the fundamental way that the Boon Nano works, being an unsupervised learning technology, when I say inference, this step is really kind of the inferencing and training steps all in one. So if we're still learning clusters, that's included in there. And so that's kind of why we have this wider standard deviation in that inference time. So this essentially means that we can handle a maximum sample rate up to 25 kilohertz, which is pretty impressive. And for this example, with this data stream that I was testing with, this produced around 50 clusters. And I'll note that there is a slight penalty for inference time as we add more clusters. Obviously, our model gets richer and our inference time increases. So this plot below kind of shows that increase in inference time as cluster count grows. So we have a factor of about 0.16 for that. We also wanted to examine the performance of AMBER on even smaller, lower power platforms. So we have also tested AMBER on an ARM M4 chip with a 240 megahertz clock. I believe this was a STMicro F4 series chip. Again, using the same data stream that produced around 50 clusters, we had an average inference time down around 165 microseconds with a slightly wider standard deviation. So this means that even on these smaller, lower powered platforms, we can support data rates up to around 6 kilohertz. So for those kinds of applications, that's still within the working range for a lot of sensors. So I should also mention that for our standard embedded AMBER device, we cap the max clusters at 1024. So with that limit, we utilize around 2 megabytes of our external SD-RAM. And for our internal SD-RAM, we're using about 73 kilobytes, so pretty low there. Obviously, this number can increase. We can accept larger numbers of clusters, but we found that for most applications, 1,000 seems to be a sufficient limit for a lot of these single sensor and sensor fusion data streams. And then, so we can also decrease the number of clusters if need be to fit inside the internal memory footprint of a given processor. However, this does decrease kind of the richness of the model that we can produce. So there's trade-offs there if we want to, have a board that doesn't have that external RAM capability. So so hopefully this gives you a sense of kind of how we run at the edge and kind of the inference rates we can support there. and I'll pass it back to Brian.
Thanks, Rod. So just a quick summary that Amber builds a customized inference engine for each individual sensor stream. It does that in real time without any human insight or intervention. It operates fully autonomously in its monitoring mode. It's scalable, obviously. So those three things that I just mentioned mean that it's scalable, right? Deploying this on one sensor is as easy as deploying it on 1 million sensors. And it also is deployed here exactly and entirely at the edge. So with that, I'll turn over to Rajan and see if there's any questions.
Yeah, Brian, there are a couple interesting questions. The first one is, if during the training process, if Boon Nano sees some anomalies, then what is the effect of those anomalies on the training phase?
Yeah, that's a good question. That's a question that does come up when people start to understand how it works. And there's actually an example of that in one of the earlier slides during one of the examples. The answer to that is that even during the learning, it looks like an anomaly. So what you end up with is in the inference model, you have some clusters, some few number of clusters that are there representing that anomaly, which is not ideal, but it will still be an anomaly if it comes up again during the monitoring phase. The worry people have is that, oh, you learned an anomaly during your training, so now it's not going to be detected. That's not the case. If it's an anomaly in the training, it will be seen as an anomaly of infrequency during the
So that would be represented by a particular cluster ID?
Yeah, usually more than one, usually,
okay.
5, 6, 7 clusters.
Okay, okay. And we have seen some examples where there has been use of like one sensor or maybe one kind of sensor, I would say. Can it work with the sensor fusion data?
It can work with sensor fusion. So that data, it can be fused before it gets to the microcontroller or fused on the microcontroller. And Rod, I think, mentioned a couple of the different pathways for that type of data.
Okay. When does Umber declare that the learning has been completed?
There's four of these. We sometimes call these graduation requirements. When the learning is done, and one of the obvious ones that you can see from the examples is this learning curve itself, right? When the slope of the learning curve becomes very flat, that is an obvious threshold that you can create to say, okay, I think we can stop learning now.
Okay. There was a graph in the previous slide, which was discussed by Rodney. Why it was not monotonically increasing? Like what can explain the decrease in the inference time at 12th or 15th cluster, as we can see here, compared to 8th or 9th cluster? Like why it is going down and then going up and then?
Yeah. I'll take that one, Brian. There's basically, it's not a perfect study because I have to basically create synthetic data that will create that number of clusters in the analog signal, and so that can vary where a given cluster sits in our model, and so there's a slight variation based on where a given cluster sits in the model and how long it takes to inference that. So
okay,
it's not
typically what we should be. Okay, so typically what we should be looking at the trend and not unlike an individual. Okay,
something like this is what you kind of expect to see, right?
Yeah. See, that explains that linear fitting equation explains the trend. Okay. I think is Boon Nano research paper or something is available to study, or is it?
So this is a core technology of our company. Yep, it's we have 3 patents around the technology. It is a novel technology. All right. So this is I've worked with most of the unsupervised machine learning technologies in my career, and Boon Nano works differently. And that's one of the reasons why I'm here now instead of academics here at Boon Logic. we certainly are interested in engagements with people that think this may be an enabling technology for them, and we can talk about licensing and so forth.
Okay. Okay, some more questions, but they would be posted on the forums. In the interest of time, we are not taking them. Thank you, Brian and Rodney, for the interesting talk. Very interesting, very impressive results. And now it's time to thank our tinyML tech sponsors. ARM is our strategic partner, and it is a software and hardware foundation for tinyML. You can see here. We have DeepLight. They use artificial intelligence to make other AI systems faster, smaller, and more power efficient. We have Edge Impulse, which is democratization of the tinyML for all the developers. They have edge, it works with the edge devices, testing pipeline, impulse, and datasets. Maxim Integrated, their new Max 78,000 implements AI inference at over 1,000 times lower energy than other embedded platforms. And it can really accelerate the tinyML never as it was never before. Kixo's AutoML for embedded artificial intelligence. It's an automated machine learning platform that builds tinyML solution for the edge using sensor data, including embedded devices as small as M0. And Reality AI is an AI platform for building tinyML products. And SceneSense, which builds ultra low power sensing and inference hardware for embedded mobile and edge devices. They design real-time systems which are always on for smart sensing, audio, vision, IMUs, and biosignals. Our next tinyML talks, December the 8th, Ian Campbell from OnScale would be presenting on training embedded AI ML systems using synthetic data, and Sakya Singh Dasgupta will be presenting AI to design energy efficient AI accelerators for the edge. Sakya Singh is from ARM Cortex. For opportunities for presentation in the tinyML, please write an email to talks@tinyml.org. Thank you, everyone.